Hello everybody and welcome. In today's video we are going to be talking about how to find the area of pretty much every shape you may run into in your geometry class. So first of all, let's talk about a little bit what is area. Now area is the total number of square units taken up by your shape. Okay, so if we have a shape like a rectangle, if we have a rectangle, what is the area of this shape? And now this is a pretty elementary example, but if we divide our rectangle up into a bunch of square units, we will be able to find its area. So that's what we're doing now. We're dividing our rectangle up in these vertical and horizontal lines. And now let's count up the number of squares that have appeared. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21. So the area for this rectangle is 21 square units. So we're going to say units squared. Whenever you find the area of your shape, your units is always squared. So the formula for the area of a rectangle is simply your base times the height. Now the base is the length of the bottom part of your shape, and this length is 1, 2, 3, 4, 5, 6, 7. It has a full length of 7, and it has a height of 3. And we know that 7 times 3 is equal to 21. And again, if our units was given, if this was, say, a length or a base of 7 centimeters and a height of 3 centimeters, then our area would be 21 centimeters squared. Excellent. Moving on, another shape you're going to run into quite frequently is a circle, and the area for a circle is given by pi times your radius squared. Now, your radius of a circle is the distance from your center point to an edge of your circle. And here, let's say that our radius is something like 5. If our radius is 5, what would our area be? Well, we just use our formula, area equals pi times the radius squared. And we plug in 5 for the radius, such that we have pi times 5 squared. And so whenever we compute 5 squared, we get 25. So pi times 25 is our area, but conventionally you would write it as 25 pi. Again, if units is given, if we said this is 5 inches, then our area would be 25 pi inches squared. Excellent. So next, let's talk about how to find the area of a sector of our circle. Let's say that some other radius is given. Of course, all radii will be equal to one another, so this would also be 5 inches. And let's say the angle between our two radii is 120 degrees, and we want to know the area of this sector of our circle. How can we find this formula? What is this formula? So it's pretty easy, actually. So while the area of our circle is pi times our radius squared, the area for the sector of our circle is going to be theta over 360 degrees times pi r squared, where theta is the angle in question. So the area of this sector would be what? Well, since theta is 120 degrees, it would be 120 over 360 times pi times our radius squared. Again, our radius is 5. And so we just multiply it out. 120 over 360 is 1/3. So we have 1/3 times pi times 25. Now we can put it all together to have 25 pi over 3 for our area. Again, if our units is given, in this case it's inches, we're going to write our final answer as 25 pi over 3 inches squared. So there is how you find the area of both a circle or the sector of a circle. Next, we have a bunch of triangles, and believe it or not, there's actually 4 formulas in order to find the area of a triangle. So most of you are probably familiar with our most basic formula, 1/2 times base times height, also base times height divided by 2, same thing. If we're given an equilateral triangle, then we can use the formula area is equal to the square root of 3 divided by 4 times the side length squared. Sometimes we are given just 2 side lengths, some A and some B, and then some angle in between theta, and there we can use the formula area is equal to 1/2 times A times B times the sine of theta. And then lastly, we have our last formula is something that's called Heron's formula. And you probably learn about this at the very end of your geometry class. It's not used too often because by this point you'll have learned some basic trigonometry, and if anything you would be using this third formula. But let me go ahead and tell you what it is. So Heron's formula is used whenever we have all 3 sides of our triangle. So first let's define what S is. Now S is equal to A plus B plus C, all divided by 2. It's 1/2 of your perimeter. And then the area formula, it's kind of a long one. The area is equal to the square root of S times S minus A times S minus B, all times S minus C. And again, this is all under your square root. So here are the 4 formulas for area of a triangle. Now let's check out some practice examples. So tried and true, our area formula equaling 1/2 times the base times the height. Here, if we have some right triangle, just this bottom portion here is going to be the length of our base, and then the height is of course just this, the height of our triangle. So if we are told that the base of our triangle has a length of 5 and the height of our triangle has a length of 8, then we can just plug those values in to our formula and have that area is equal to 1/2 times 8 times 5. 1/2 times 8 is 4, and 4 times 5 is 20. So the area for this triangle would be 20 square units. Again, you can always say units squared. Now sometimes you're not given just a nice right triangle, but you can still use this simple formula. So let's look at an example of how that would be. So let's change our shape up just a tiny bit. Let's say we have just a triangle that looks something like this. And here, they give us our height. We'll call it 6. And then they say this length here is also 6. And then this length is 3. What would we do to find the area for this shape? Well, I'll change colors. So the height is given to us to be 6, but our base length is the sum of these two values. Our base length will be 6 plus 3 to give us 9. So the area for this triangle would be 1/2 times 6 times 9. 1/2 times 6 is 3, and 3 times 9 is 27. So the area for this triangle is 27 units squared. Excellent. So moving forward, we have our equilateral triangle. Remember, our equilateral triangle is such that all of the sides are congruent to one another. And the formula for the area of an equilateral triangle is the square root of 3 over 4 times our side length squared. So let's say that our side length is given to us to be 10. What would the area of this equilateral triangle be? Well, we can simply plug in 10 for our side length and have that our area equals root 3 over 4 times 10 squared. Whenever we simplify, we have root 3 over 4 times 100. 104 simplify to give us 25 times the square root of 3 for our area. So here's how you can use this formula to calculate the area of an equilateral triangle. Now, I would be remiss to not mention that you could still use your base times height divided by 2 formula. However, in order to use this other formula, you need to be, so if we want to use area equals 1/2 times base times height, you need to be familiar with your special right triangles. You need to recognize that, hey, this is an equilateral triangle. So if I drop down this perpendicular bisector from our top vertex, both of these angles will be right angles. And since it's an equilateral triangle, all of the angles are equal to 60 degrees. And so I can use my knowledge of special right triangles to determine that this side length is 5 and our height is a length of 5 times the square root of 3. Now, so let's clean up. So we found our area already to be 25 times the square root of 3. Let's verify that with this other area formula. So we know that our base, so we have area equals 1/2 times base times height. We know that our base is 10, and we know that our height is 5 times the square root of 3. All right, so 1/2 times 10 is 5, and 5 times 5 is 25, and we still have our square root of 3. So as you see, it doesn't matter which formula you use, you will get the area. Very excellent. Let's move forward to another type of triangle. So here, this formula for a triangle is that our area is equal to 1/2 times A times B times the times the sine of theta. And it's important to know that for this formula, you have some A and some B, and the theta in question is between your A and B. All right, so you do not use this formula if you have some angle here and only these two angles are defined. Theta must be between A and B in order to use this formula. So let's try it out. Let's say that theta is equal to 60 degrees. Let's say that A is length 7 and B is length 6. In order to find the area of this triangle, we can use this formula and have that our area is equal to 1/2 times 7 times 6 times the sine of 60 degrees. All right, so our area is going to be equal to, well, 1/2 times 6 is 3, and 3 times 7 is 21. So our area will equal 21 times the sine of 60 degrees. Now we need to determine what the sine of 60 degrees is. And in order to do this, we can think to our special right triangles. So let's draw a special right triangle such that this is 30 degrees and this angle down here is 60 degrees. You know what? Let's make this bigger. Let's move it over here. Let's shift it over here. Make it bigger so we can clearly see what's happening. So this is 30, this is 60, this is of course 90. So opposite the 30 degrees you have some side length, opposite the 60 you have some side length √3, and your hypotenuse is 2 times the side length. We're looking for the sine of 60 degrees. So think to SOHCAHTOA. Remember that sine is opposite over your hypotenuse. So for 60 degrees, our opposite side is s√3. So we have s√3 over our hypotenuse of 2s. And so this cancels out. The s's cancel to leave you √3 over 2 for the value of sine of 60 degrees. So we just plug that in to our area formula. We have 21 times √3 over 2. And that's your final answer. It doesn't simplify anymore. You can also, of course, write it all together as 21 times √3 over 2. Excellent, excellent. So that is how you use this area formula for a triangle. Lastly, we have Heron's formula. And this formula, again, we have some A, B, and C. Let's say that we have 5, 6, and 8. So we have our side lengths of our triangle, and we want to determine the area. Of course, if you know trigonometry, you can use it to find an angle measure, and then you can use the previous formula to find the area. However, if you're tasked to solve the problem using Heron's formula, again, what is it? Well, first we need to define what S is, and S is 1/2 of our perimeter. And then Heron's formula is the full square root of S times S minus A times S minus B times S minus C. This is Heron's formula. So plugging in these values, first let us find S. So our perimeter is 5 plus 6 plus 8, all divided by 2. 5 plus 6 is 11. 11 plus 8 is 19. 19 over 2 is 19/2. And you know what? I want to make this problem easy for us. So let's change this longest side to be 9. And so whenever we solve to find S, we see that S is equal to 10. Let's make the math easy on us here. Next, we want to find the area. So we're going to plug it into this long formula. Area is equal to the square root of 10 times 10 minus 5, which is 5, times 10 minus 6, which is 4, times 10 minus 9, which is 1. All right. So we have 10 times 5 is 50, and 50 times 4 is 200. So our area is equal to the square root of 200. Of course, this simplifies to be 100 times 2, so we can pull out the 10. So 10 square root 2 is going to be the area for this triangle. And that is how you use Heron's formula. Excellent, excellent. Next, we're going on to quadrilaterals. Here we have a parallelogram. Now, a parallelogram, its formula is just like a rectangle. It's found by the area being equal to your base times your height. So if we have a length of our base, let's call it 10, and we are given the height, let's say it's 5, then our area is simply going to be equal to 10 times 5, which will be 50. However, whenever you're solving area problems, it's not always that simple. Sometimes they might say, hey, our base is 10, this length is 5, and you know what? Here, let's define it more. The full base is 10. However, we know that this portion is 3, and this full portion here is 7. And we want to know the area of our parallelogram. And what can we do? Well, in order to find the height of our parallelogram, we need to use Pythagorean's theorem. And recall that Pythagorean's theorem is a squared plus b squared equals c squared, where c squared is the hypotenuse of your right triangle. So we can plug in these values to have 3 squared plus our unknown b squared equals 5 squared. So 9 plus b squared is equal to 25. Therefore, b squared, when we subtract 9 from both sides, is equal to 16. And the square root of 16 is 4. So we found that our height of our parallelogram is 4. Now we have our base and our height, so we can use our simple base times height formula to get that 10 times 4 is 40. So the area of this shape would be 40. Of course, if it gave us units, if it said our units were in centimeters, then our final answer would not just be 40, but it would be 40 centimeters squared. Excellent. Next up, we have a trapezoid. And here, let me shift it just a little bit so we can see the full shape. Excellent. So, the area of a trapezoid, how do we find it? Well, the area of a trapezoid is given by base 1 plus base 2 divided by 2 times your height. Okay? So, in order to find the area of a trapezoid, we must know the full length of our base 1 and our base 2. The bases of a trapezoid are the sides that are parallel to one another. So even if your trapezoid is turned sideways, such that your parallel sides are on the left and the right hand side, those are still your bases. So you are going to use the pair of parallel sides for the bases of your trapezoid when you're determining its area. All right, and then again, it's going to be times the height. So we need to know what our height is. So here, let's say that our base 1 was given to us as 8. Base 2 was given to us as 12, and our height was given to us as 6. What would the area of our trapezoid be? Well, we'd plug our values into our formula, and we have 8 plus 12 divided by 2 times 6. 8 plus 12 is 20. 20 divided by 2 is 10. And 10 times 6 is 60. So the area for our trapezoid would be 60 square units. Excellent, excellent, excellent. With a trapezoid, it may be like in the last problem with the parallelogram, where they give you the slant value, and then you must use Pythagorean's theorem in order to find the height. Since we already did a problem like that, we can skip it from now, but let's also talk about another way to find the area for a trapezoid. What if the trapezoid, it doesn't give you either of the bases, but it gives you this mid-segment length and the height? What if it says this mid-segment length is 10 and the height is 6? What would our area be? Well, it's important to know with trapezoids that the mid-segment is equal to the average of the sum of your two bases. So doesn't this look familiar with your area formula? So the area of your trapezoid is not only base 1 plus base 2 divided by 2 times your height. It also could simply be defined as your mid-segment length times your height. And so in this case, our mid-segment length is 10, our height is 6, so our area is 60. Excellent, excellent. Moving forward, we have our great friend the square. And who doesn't love finding area of a square, as it's just so simple? The area of our square, it is base times height, but since it's a square, all the side lengths are congruent. Therefore, you might often see the area for a square just be written as the side length squared. So if we're given that the side length of our square is, let's say, 8, then what's the area for our square? Well, it would just be 8 squared, which is 64. Excellent. How about what if for a square it gave us the diagonal length? And it said that our diagonal was length 10. If it gave us our diagonal to be length 10, what would be the area of our square? So there's actually two ways to determine this. There is actually an area of a square formula that has to do with its diagonal, and that is this. I'll go ahead and tell you. The area of a square having to do with its diagonal is the diagonal of your square squared divided by 2. This will be the area of your square. So let's plug in our values. 10 squared is 100, and 100 divided by 2 is 50. Now sometimes you won't remember this formula, so how else could we determine the area of our square given just the diagonal length? Well, it would be up to us to recognize that, hey, this diagonal is going to bisect this angle here, and since a square's angles are all 90 degrees, this will be a 45-degree angle. And same thing for this angle down here. So this is a 45, 45, 90 special right triangle. So let's recall for our special right triangles, for our 45, 45, 90 special right triangle. We have some side length, and our diagonal is some side length times the square root of 2. So since we were given that 10 is our diagonal, we're going to set s times the square root of 2 equal to 10, and then we will solve for s. And we'll do this by dividing by the square root of 2. So s equals 10 divided by the square root of 2. And now we have just the side length of our square. And then we can use our normal side squared formula. So what is 10 times 10 over the square root of 2 squared? Oops, sorry. Well, 10 over the square root of 2 squared is it times itself. 10 times 10 in our numerator is 100. Root 2 times root 2 is 2. So we have 100 over 2, which again is 50. So if you're given the diagonal of a square, you can either use the simple diagonal squared divided by 2 formula, or if you forget this formula, you can use your special right triangles in order to determine the area. Moving forward, we have our rhombus. Now, a rhombus actually has 3 different area formulas. Actually, has quite a bit. It has our tried and true base times height. It has a formula to do with its diagonals as well. It's diagonal 1 times diagonal 2 divided by 2. And then the last formula for a rhombus is the area is equal to your side length squared times the sine of theta. Okay, so here are our 3 area of a rhombus formulas. So let's use our first one first. So this one's our most simple one. If we're given a side length of 6, it will have some height. Let's call our height, I don't know, 5 root 3. And then in order to determine the area, you simply multiply the 2. So in this case, 6 times 5 root 3 would just be 30 root 3 for our area. A quick reminder, if you're not too clear on what a rhombus is a parallelogram such that all 4 of its sides are congruent. It's different in a square in that the 4 angles are not all right angles. Okay, so that's how it's different from a square. A square is a special type of rhombus. However, just like the square, it has a diagonal formula, and the reason a rhombus and a square have formulas relating to its diagonals for the area is because the diagonals of these shapes intersect at a perpendicular. They intersect at right angles. So the angles formed by the diagonals are right angles. And that's why these formulas exist. Later on, we're going to be talking about the area formula for a kite, and that has to do with its diagonals as well. And it's again because the diagonals intersect at a perpendicular. So here, if we're given that the diagonal for diagonal 1 is 10 and diagonal 2 is 11, what would the area for this rhombus be? Well, it would just be 10 times 11 over 2, which would be 110 over 2, which is 55. So that would be the area if we were given its diagonals. And then lastly, what would be the area if we were told that the side length is 10 and this angle here is 70 degrees? Well, it would simply be we would use our last formula, and our area would equal 10 squared times sine of 70 degrees. Now I don't know what sine of 70 degrees is off the top of my head, but we could use a calculator to figure this out. So here we have 10 squared, that's of course 100, and 100 times the sine of 70 degrees has a value of 93.9. So this is equal to 93.9. Now some of you may be curious or asking the question, okay, but there's different angles given in a rhombus. If this is 70 degrees, then that means this angle over here would be 110 degrees because these angles are supplementary with each other. So which angle would I choose? And the short of it is, it doesn't matter which angle you choose because sine of 70 and 110 are going to be the same value. But let's just verify it again with our calculator, and that if we had the area and we chose 10 squared times the sine, but instead of 70 we chose the other angle of 110 degrees, let's verify that we get the same value. And I said this was 0.9. Hopefully it's still up in the calculator. So we have our calculator. We're going to have 100 times the sine of 110 degrees and we get 93.9. We get the exact same value as whenever we used the sine of 70 degrees. And again, just so y'all can see it, I will clear it and do it one more time. 100 times the sine of 70 degrees equals the same value. So it doesn't matter which angle you choose in this case. Moving forward, now we have our kite. Again, I kind of hinted at it, but the area of a kite has to do with its diagonals, and it is the same as that second formula for the rhombus. It's diagonal 1 times diagonal 2 divided by 2. And then you can also use this trig formula for the area of a kite, and that is a times b times the sine of theta. Now notice the only reason this formula is different than our previous rhombus formula is that in a rhombus all the side lengths are equal, whereas in a kite the side lengths are different. So that's why the second area formula looks a little bit different. It's really the same formula. It just looks different because the side lengths of a kite can be different. So in a kite, the diagonals, again, they bisect one another, and that is what allows for this form, or they don't bisect, they meet at a perpendicular, and that's what allows for this formula. And if we are given that this longer diagonal is some length 15, and this shorter diagonal is some length 8. In order to determine the area for this kite, we're going to do area equals 15 times 8 divided by 2. We can simplify. 8 cancels with the 2 and we're left with a 4, and 15 times 4 is 60. So our area of this kite is 60. Again, if we had the units, don't forget this, it would be 60 inches squared. Okay, and then this second formula for a kite, if we had the side lengths, if we had some side lengths, say that this is 8 and this is 15, and that this angle here is some 120 degrees. What would the area be now? And I do want to point out, it is important that with a kite, whenever you're using this second area formula, your A and B must be different values. Okay, so if you're not clear on this, a kite is a shape such that it has two sets of congruent sides. In this case, they're adjacent to one another. So this length down here would also be 15, and this length would be 8. However, you could not use this formula if with some angle here. Oops, that green doesn't really work on this shape. If you have some angle here, let's call it 60, this will not, you can't use 8, 8 and sine of 60 for this formula. You have to choose the two different side lengths, and you have to choose the angle between those two side lengths in question. If you think back to your triangle formulas, the reason this formula is here, this is the exact same thing as your third triangle formula, except for the fact that it's not divided by 2. And that's because this is essentially, a kite is essentially two congruent triangles pushed up against one another. Look at this middle diagonal. Here, this diagonal divides our shape into two congruent triangles, whereas the other diagonal, this one here, it divides our shape into two triangles, but these triangles are not congruent. Okay, so that's why we must choose this side length, the two different side lengths, and then the angle in the middle of them. All right, so using this formula, we have our area is equal to 15 times 8 times the sine of 120 degrees. So 15 times 8 is 120. And then sine of 120 is something I'm not sure about. I could figure it out, but let's just use our calculator. So we had 15 times 8 times the sine of 120. And we get 103.9 for our area. 103.9. Excellent, excellent. So there is how you can find the area for your kite. One of the last shapes we're going to cover is not just a hexagon, but any regular polygon. Okay, so these formulas work for any regular polygon. Again, a regular polygon is a polygon such that all of the sides are congruent with one another and all of the interior angles are congruent with one another. So there's two formulas to talk about. One formula is 1/2 times the apothem times the perimeter. Now your apothem is defined to be the distance from the center of your shape down to the bottom such that it forms a perpendicular and splits your side length in half. So let's say that our apothem is equal to, we've been using 8 a lot, let's keep it. Let's say your apothem is equal to 8, and let's say our side length is equal to 10. What would be the area of this shape? And actually, here, let's not use 8. Let's use 5 square root 3. This is just more accurate. So what is the area for this shape? Well, we have area equals 1/2 times our apothem of 5 root 3 times our perimeter. What's the perimeter of our shape? Well, it is 10 plus 10 plus 10 plus 10 plus 10 plus 10. So that's 60. So 1/2 times 60 is 30. So we have 30 times 5 root 3. And 30 times 5 is 150. So we can see that the area for our shape, for our regular polygon, is 150 times the square root of 3. Okay, so sometimes they don't give you the apothem. So what would be the area formula if you didn't have your apothem handy? And it's kind of a long one, but it is n times your side length squared divided by, actually I'll write it this way, divided by 4 times the tangent of 180 over n. Okay, and if you'd like to know why this is the formula, I have a separate video going into detail about why this formula works for the area of a regular polygon. Feel free to check out that video. But let's just take it for granted here and let's show it in action. So in this case, let's keep our side length of 10, but let's say we don't know the length of our apothem. So n represents the number of sides in your regular polygon, and s represents the side length of it. So in this case, we have our n is 6 because we have a hexagon. Our side length is 10, so 6 times 10 squared, all divided by 4 times the tangent of 180 divided by 6. That's going to be 30, so the tangent of 30 degrees. And we need to now simplify this. So we have 10 squared is 100. 100 times 6 is 600. So we have 600 over 4 times the tangent of 30. So we can use our special right triangles to find the tangent of 30 degrees. But I'm just going to go ahead and tell you it's 1 over the square root of 3. And now we can simplify. 604, they'll of course simplify to give us 150 up top. So our area is equal to 150 divided by 1 over the square root of 3. Dividing by a fraction is the same thing as multiplying by its reciprocal. So we're going to multiply by the square root of 3 over 1. And of course, this just gives us 150 root 3. And as you can see, this is the same value as we had just a moment ago. So there are your two formulas to find the area of any regular polygon. We're nearly finished. We also sometimes are tasked with finding the area of the shaded region. So what would we do if we needed to find the area of this shaded region? Well, we would need to find the area of our circle and subtract the area of our triangle. And this would give us the area of our shaded region. So let's say that this triangle has side lengths of 5 in that it's a right triangle. We know that the area of our circle is pi times the radius squared, and we know that the area of our triangle is base times height divided by 2, or times 1/2, and this will equal the area of the shaded portion. So our radius in this case is 5, so we have pi times 5 squared minus base times height. Base times height, those are both 5. So minus 5 times 5 divided by 2. This will equal the area of our shaded region. So we have 25 pi minus 25 over 2 equals the area of our shaded region. We could, of course, factor out a 25 and write it something like this: 25 times pi minus 1/2 is equal to the area of our shaded region. And of course, we could plug this into a calculator to get a more exact value, or not more exact, but a number value instead of this set of equations. But we'll leave it as this. And then lastly, let's talk about some composite shapes. Okay, with composite shapes, we need to, well, first let's define some side lengths. Let's say this is length 7, this is 6, 5. Let's call this full length 10, and let's call this bottom part 15. So here we need to break up our shaded, we need to break this up into a bunch of smaller pieces that we know how to find the area for, and in order to find the area of this full thing. So what I see here is I can break this up here. Here, this is a trapezoid. Of course, this is a right trapezoid. These are going to be right angles. Then I have a rectangle. I have this rectangle. And then up top, I have this semicircle, or this half circle. I have this half circle. Okay. So what are the dimensions of our rectangle? Do we know them? Well, we know that it has a height of 10, but what about this distance? What is this distance here? Well, if this full length is 15, and this part is 7, well, hey, we might not know this yet. What about this height? What is this height here? Well, this height must be 4, because if this is 6 and the full distance is 10, then this height is 4. So now we have enough info to find the area of this trapezoid. So what is this trapezoid going to be? Remember, trapezoid is base 1 plus base 2 divided by 2 times the height. So we have 7 plus, oh, check this out. I was about to write 15, but it's not 15. We know this distance up top is 5. And if this full distance was 15, then this part is going to be 10. So our base 1 is 7. Our base 2 is 10. We're going to divide that by 2 and multiply by our height of 4. So 7 plus 10 is 14. 14 divided by 2, or I'm sorry, it's 14. 7 plus 10 is 17. So we have 17 divided by 2 times 4. Of course, a 2 cancels with one of the 2's here, and we're left with 34. So this trapezoid has an area of 34 square units. Now to our rectangle. We did have enough information because the length was up here. It was 5, and it has a total height of 10. So let's change color for our rectangle. Here, I'll write it in this green color. Be consistent. So for our rectangle, we have base times height. So our base is a length 5, and our height is length 10. So our area for the rectangle is 50. And then lastly, we have our half circle. So the area for our circle is pi times your radius squared. So we have our full length, we have our diameter. Your radius is half your diameter, so our radius in this case is 2.5. So we have pi times 2.5 squared. But before we calculate this, let's ask the question. This is the area for a full circle. We just want a half circle. So half a circle will have half the area. So we're going to divide this by 2. Earlier we mentioned this segment circle formula, which is the angle measured over 360 degrees. Well, the angle of a straight edge is 180, and 180 over 360 simplifies to 1/2. So you can use either method or either thought process to get the fact that you're going to put your circle formula over 2. So 2.5 squared is 6.25. So let's just put this into our calculator. We have 2.5 squared divided by 2 is 3.125. So this is equal to 3.125 pi. Lastly, if we want to know the total area, we need to sum all of these values, the 34, the 50, this was equal to 50, and the 3.125 pi. 34 plus 50 is 84. 84 plus 3.125 is 87.125. And then, of course, well, really, we can just add these two. So we have 84 plus 3.125 times this pi. We can't combine the 84 and the 3.125 because there's not a pi here. So this would be your final answer. If you wanted a number value, you would just punch that into the calculator and get it. But there you have it. There is how you find the area of all the shapes you may run into in your geometry class. I hope you found this video helpful. If you did, hit that subscribe button, leave me a comment down below, and I will see you in the next video.